All right, this video is going to expand some more on reference angles and trigonometric functions. So when we're in the first quadrant, the angle that you create is the same as your reference angle. However, when you get into quadrant 2, if you notice my T here, then when I want to reference this point in the plane, I'm going to then drop my perpendicular down to the x-axis and then use this acute angle here as what I'm going to call my reference angle. If I'm in the third quadrant, then again, I'm going to take that point in the third quadrant and then I'm going to drop this to the x-axis so that way I have like a negative x, negative y point that is represented here. Here would be a negative x, positive y point. If I'm in the fourth quadrant, okay, then my reference angle I'm going to take, I'm going to drop a perpendicular to the x-axis, and in that case it would be a positive x and a negative y. And so that way we can track any of these obtuse angles back to an acute angle, and we know trigonometric functions of acute angles, specifically our 30, 45, and 60 angles. So in this next part here, we're just going to look at the different reference angles, and then we're going to just find sine, cosine, and tangent of that angle. So here in A, if I have my starting side here, and I label, especially when I have to go backwards this way, so negative 120 would be 30 degrees past 90 degrees. And so this is my angle theta. But my reference angle, remember, drops to the x-axis like so. So this is the point, negative x comma negative y. And so I want to make sure that I am representing that point with an acute triangle that is horizontal to the x-axis. Okay. All right, so negative x, negative y. And then I'm just going to call this here because we don't know it quite yet. We're going to call this the hypotenuse. So this triangle here, if I were to remap it, would have a 60-degree angle as my reference angle. So my theta prime is what we call that, is 60 degrees. Now I found that because if I were to then transfer from 120 all the way to 80, that piece right there would be 60 degrees. So I'm just going to remap it there. I know from special right triangles that my ratio is 1 for the smallest leg, 2 for the hypotenuse, and √3 for the largest leg. I can now find the sine of negative 120, the cosine of negative 120, and the tangent of negative 120 using this as my reference angle. Let's be very careful and make sure that I label this as negative 1 and negative √3 just because of its position here in the quadrant 3 position. And so sine is going to be negative √3 over 2. Cosine is going to be negative 1 over 2. And tangent is going to be negative √3 over negative 1. All right, part B wants us to look at 5 pi over 6, excuse me. So here is my initial side. Now, if I were to remember all the way around is 2 pi. So halfway around in terms of radians is pi. And my y, my positive y-axis would then be pi over 2. If I want to try to find 5 pi over 6, I need to divide up my angles so that 6 of them get me to here, or that this is 6 pi over 6, because that's pi. Therefore, this would be 1 pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, 4 pi over 6, or 5 pi over 6 is this angle, and I'm going to drop that down. Well, if that's my theta that I'm looking at, then my reference angle, or my reference triangle, only has a pi over 6 left over to get me down here, or a 30-degree angle. I already had that triangle measure here. I'm just going to flip it so that it's correct for that, so that the small side is across from the 30-degree angle. And then let's make sure that we make this the negative x and positive y, since I'm in the second quadrant. I can then find the sine, the cosine, and the tangent of 5 pi over 6 using my reference triangle right here. So positive 1/2, cosine is negative root 3 over 2, and tangent is 1 over negative root 3, and I'm not going to worry about rationalizing the denominator here. All right, 7 pi over 4. I'm going to use that same kind of setup here to know that all the way around would be 2 pi radians. Half of the way would be pi. Well, pi would be 4 pi's over 4, and 2 pi would be 8 pi's over 4. Therefore, if I need 7 pi over 4, I'm going to say that this is 5 pi over 4, 6 pi over 4, which is 3 pi over 2. And so 7 pi over 4 is going to be right here. 7 pi over 4 being in the third quadrant, and then I map that to the positive x quadrant. One thing about all the over 4 angles is they do divide my quadrants in half. So this is going to be a 45-degree angle, or pi over 4. So then I can draw that isosceles right triangle over here. I know that this is 1. I'm going to go ahead and say positive x, negative y, since I'm in quadrant 2, so negative 1. And my hypotenuse is the square root of 2. I can then find the sine, the cosine, and the tangent. For, remember, this angle, I'm just using this triangle with the angle of pi over 4 as my reference triangle or reference angle. All right, so sine is negative 1 over root 2. Again, I'm not going to worry about rationalizing the denominator. Cosine is positive 1 over root 2. This is my angle I'm using. And then 7 pi over 4 tangent would be negative 1 over 1. All right, last example wants us to do 210 degrees. All right, so if this is 0 degrees or 360 degrees, and this is 180 degrees, then 210 degrees would be 30 degrees past 180. And if you notice, we actually already did this one, kind of. We did it in the second quadrant, okay, but it's going to be the same type of reference triangle. To drop this here, but I've already done a triangle for a reference of 30 degrees. I have a negative x and a negative y in this case. So 1, 2 root 3 for my triangle proportions. Across from 30 is 1. And then I'm going to make sure my negatives go with my x's and my y's. And then again, I can find the sine, the cosine, and the tangent for that angle using our reference triangle right here. So sine would be negative 1 over 2, cosine would be negative root 3 over 2, and tangent would be negative 1 over negative root 3, and I'm not going to worry about rationalizing the denominator there.